everyone, welcome to part 4 of chapter 18. Today we are going to continue our talk on Gibbs free energy, and we're going to look at the change in Gibbs free energy at non-standard conditions. So what we've done thus far is we've calculated the Gibbs free energy change at standard conditions. So when we have 1 atm of pressure for our gases, or we have 1 molar for our aqueous solutions, right? But now we're going to look at how does a difference in pressure or the difference in concentration affect our change in Gibbs free energy? So first off, though, I want to talk about this term free energy, right? We haven't addressed that yet. Why is it called free energy? Well, free energy is the maximum amount of energy released from a system that's available to do work on the surroundings, okay? We know that sometimes during these reactions, some of our heat that's being released due to the enthalpy change goes into increasing the entropy of the surroundings, so it's not available to do work, right? Some of this free energy is lost due to heating up the surroundings. So not all of the energy from our reaction, even a spontaneous reaction or even an exothermic reaction, is available to do work because some of it is being lost as heat. So we're looking at the amount of energy that is free to do the work. So that's why it's called Gibbs free energy. So if we take this as an example, right, we have graphite reacting with hydrogen gas to produce methane. And so this is an exothermic reaction, so heat is being released. We have a negative value for delta S because our moles of gas is decreasing, right? We have 2 moles of gas on the left and only 1 on the right. So our moles of gas are decreasing, so this would be unfavorable in terms of our change in entropy. But overall, we have a spontaneous reaction because we can calculate it using that delta G equals delta H minus T delta S, and it will still come out as spontaneous. But if we look at what's happening, right, we have an exothermic reaction, but some of our energy is being lost as heat to the surroundings. So the maximum amount of work, it does not equal, the heat released, right, from the reaction, because some of it is available to do work. Some of it, though, will just be lost as heat. So that is why we're seeing this difference in energy, because some of it's being lost as heat to increase the entropy of the surroundings. So in a real reaction, a lot of that free energy that we calculate is not even available to do work. A lot of that free energy, even though it's taking into account some of the energy that's being lost, even more of it beyond that is being lost as heat. So this is our light bulb example we talked about earlier, right? If we input 100 watts of electrical energy, we get about 5 watts out as light, and the rest of it is dissipating as heat. Same kind of thing here if we use, our battery to, make our motor go, right? Some of it will be lost as heat, so not all of it is available to do work. Okay, this is why real reactions are irreversible, because some of it's being lost as heat that we can't get back. It's just leaving. Okay, let's talk about standard free energy change. That's what we've been looking at thus far. So delta G naught with that 0, that's telling us it's the standard free energy change. And that's the change in free energy that will occur if the reactants in their standard states are converted to the products in their standard states. So this is, in the phase that they normally exist at room temperature. Usually we're at 25 degrees Celsius here. And it will be 1 atm of pressure for gases. It will be 1 molar for concentrations. Okay. When we are looking at delta G, we can start to think about this in terms of an equilibrium, or for reversible reactions, right? And if it's really negative, right, the more negative the value for delta G, the more spontaneous it is, essentially. The farther to the right the reaction will proceed in order to achieve equilibrium. So if we have a really negative value for delta G, that's going to tell you we have a really large value of K, that we're making a lot of products. So as you can see here, we're going to start relating this to some of the other chapters that we've looked at in the course. Okay, so delta G under non-standard conditions. So it's important here to figure out whether you're using delta G or delta G naught, okay, because they are different. So delta G naught, right, with the 0, that's telling you it's at standard conditions. 1 molar for our concentrations, 1 atm of our pressure, and their normal state at that temperature. Like water would be a liquid, right? But delta G can be for any time. That would be non-standard conditions. Okay, so we can relate delta G and delta G naught by this equation. Delta G is equal to delta G naught, so our standard Gibbs free energy, plus R times T times the natural log of Q. Q, if you'll recall, would be essentially like our equilibrium constant, but it's when it's not at equilibrium. It's called the reaction quotient, but we calculate it the same way, right? It's products raised to the power of their coefficients over the reactants raised to the power of their coefficients. This R value is going to be 8.314 joules per mole Kelvin. We will typically use it, though, when we're using this, we're going to use it as 0.008314 kilojoules per mole Kelvin because our delta G is in kilojoules. Okay, and that's just the easiest way to make all of our units match. You can also do it as you can convert your delta G's all to joules. That's fine too if you don't like working with decimals. Either way, doesn't matter, just make sure your units match. And then our T here is going to be our temperature in Kelvin. Okay, so it's taking into account a difference in temperature potentially and a difference in concentrations or pressures. When we are at equilibrium, okay, delta G is going to be 0. Okay, so this will be 0. So if we rearrange our equation, then we'll get delta G naught is equal to minus RT times the natural log of K. So we're using K here now because we know we're at equilibrium. Okay. Otherwise, like I said, we're using that same equation. You're just going to put 0 in for delta G and then solve for delta G naught. So if we look at the relationship between delta G and K here, if K is greater than 1, then that's going to make delta G negative. Okay, so we're going to relate this, right? Delta G is negative. That's telling us that our reaction is spontaneous in the forward direction. That is the same thing that we learned when K is greater than 1, right? When K is greater than 1, our reaction proceeds in the forward direction. And the larger the value for K, right, the more the products are being favored over the reactants. The same thing is true for delta G. The more negative the delta G value, or the delta G naught value, the farther our reaction will proceed to the right. So here it is kind of summarized. If we have a reaction that's proceeding spontaneously to the right, so it's going to make a lot of products, Q is going to be less than K, right? Because that means we have too few products or too many reactants, so we need to go to the right. And if we go ahead and we, calculate all that out, we're going to get that delta G is less than 0, right? So delta G will be negative, which is also telling us to go to the right. So you can look at either one of these things, right? You can look at our relationship between Q and K, or you can look at the value for delta G. The opposite is also true. If we have Q greater than K, then that means our reaction will go spontaneously to the left, right? It will shift to the left. Q is greater than K because we have too many products. This would be related to a positive value of delta G. It will go spontaneously to the left, right? Or the reverse reaction is spontaneous. And then if our reaction is at equilibrium, then that means Q is equal to K, right? We remember that from earlier. So if you did their ratio, you'd get Q over K is equal to 1, and that will cause delta G to be equal to 0 at equilibrium. So in looking at this, right, here is our equilibrium when Q is equal to K. And that is going to be the minimum free energy, right? That would be delta G is equal to 0. So at all other places, delta G is not equal to 0 because we are not at equilibrium. And the farther away we get from equilibrium, right, like the farther we go this way or the farther we go this way, our value, right, our absolute value for delta G is going to increase. Delta G is essentially telling you kind of, how far away you are from the equilibrium value. So the smaller your delta G value is, the closer you are to equilibrium, whereas the farther away you are, the larger it is. And this is the absolute value I'm talking about. If we wanted our reaction, if our reaction needed to go to the right, then that's going to have a negative value of delta G because it will go spontaneously in the forward direction. If we needed it to go to the left, then that would be a positive value of delta G because we need it to go in the reverse reaction. All right, so just to sum up, we have our equation here, delta G is equal to delta G naught plus our RT times our natural log of Q, and that's for any conditions at all. It can also be used for equilibrium. You'd just plug in a 0 for delta G and then rearrange and solve. But if you know you're at equilibrium, then you can use that second equation, which is delta G naught is equal to minus RT times the natural log of K. And then if you had a ratio of Q versus K already, you could use that third equation there. That's kind of uncommon that you might have it, but it's not, it's not totally like it's never going to happen. So you can use RT natural log of Q over K, or when we have natural logs or logs at all and we're dividing them, then that's the same thing as taking the log of one minus the log of other. So you can break it apart that way. Like I was saying before, if Q and K are very different, right, if you're really far away from equilibrium, then your delta G is going to have a really large value. Either positive or negative, doesn't matter, but the number will be large. And that will mean that the reaction is going to release or absorb a large amount of free energy in order to get to equilibrium. If Q and K are about the same, then that means that delta G is going to have a really small value. It doesn't matter positive or negative, just the number itself will be small. And that's telling you that you're close to equilibrium and you just need to release or absorb a little bit of free energy in order to get to that equilibrium value. All right, let's go ahead and try some calculations. So this says calculate delta G at 298 Kelvin, which is a standard condition, right? That's 25 degrees Celsius for the reaction under the given conditions. So we have our reaction there, we have our delta G naught already, and then we have pressures. Okay, so as you can see, the pressures are not 1 atm. So this is telling us that we are not at standard conditions. So we'll need to use that delta G equals delta G naught plus RT natural log of Q. So here we go. Not at standard conditions, so we need to use that equation. First thing we're going to do is calculate Q. So Q is going to be just the same as we've always done it. So a lot of these will be with pressures. This is really common. This is really common that we're doing a gas reaction. Please remember, you don't use any brackets when you're doing pressures. You're just going to put P, which stands for the partial pressure, and then the substance on the bottom, so the partial pressure of nitrogen dioxide, for example, and then squared. Remember, we're always going to raise them to the power of the coefficients. And then on the bottom, right, we have our pressure of nitrogen monoxide squared times our pressure of O2. And then we can plug in all our numbers and solve for Q. And then once we've got Q, now we can plug that into our equation. Delta G naught was given in the problem, and then we will use, RT natural log of Q. Remember, you need to convert your units of R to make sure to match G or delta G, or you can, change your units of delta G to match R. It doesn't matter whether you do it in joules or kilojoules, just make sure you're keeping track of your units. And then your, temperature needs to be in Kelvin, and then we'll take our natural log of our Q value. And there it is, there is delta G. Pretty straightforward. Your turn. So go ahead and try this one. It's very much the same as the last problem. This is just to remind you how do you, calculate that Q value, dig that out of your brain, make sure you're all good to go. So go ahead and pause here, try this problem out, and then come back when you're ready to see the answers. All right, let's go through this. So we know we're not at standard conditions because our pressures are not at 1 atm. So the first thing we need to do is calculate Q. So we'll go through, calculate Q. Again, make sure you have products over reactants and everything's being raised to the power of their coefficients. And then you can calculate your Q value. And then we'll use that Q to plug into our equation. Again, make sure your unit of R is matching your unit of delta G. And then just go ahead and solve. And then we will get our delta G value. Okay, so like we talked about earlier, the equilibrium point occurs at the lowest value of free energy available to the reaction system. So at equilibrium, delta G will be equal to 0, and Q will be equal to K. So if delta G of the reaction is equal to 0 at equilibrium, then when we are using that equation we were using before, we'll set delta G at 0, and we can rearrange and solve for delta G naught. And then again, we can use K instead of Q, since we know we're at equilibrium. So if you'll recall, K is equal to products over reactants. So if K is less than 1, right, that means that K is really small. So that means our reactants are being favored in that reaction. That will give us a positive delta G because the reaction is spontaneous in the reverse reaction in order to make a bunch of reactants. Okay, that means nothing will happen with the reaction at all if there, are no products present because it needs to shift to the left. And if it doesn't have any products to make reactants, you're just kind of stuck. So essentially that would mean our reaction wouldn't go. If K is very large, right, if K is greater than 1, then that means that delta G is negative, and the reaction is spontaneous in the forward direction under standard conditions. And if K equals 1, then delta G is 0, and the reaction's at equilibrium under standard conditions. That's pretty rare. It would be rare that K is equal to 1 and delta G naught would be equal to 0. Normally, K will either be really large or K will be really small. So in looking at this, we have, on the top left, we have a reactant favored reaction. So let's say we were starting at standard conditions. So this is standard conditions where everything is at 1 atm. And if we had a reactant favored reaction, that would mean K is less than 1. And if we plugged in 1 for K, we would get a positive value for delta G, which means our reaction would proceed in the reverse reaction spontaneously. If we did, if we looked at the top right and we have a product favored reaction, meaning that K is greater than 1, if we plugged K as, greater than 1, a very large number, then we would get a negative value for Q, which is telling us that we have a forward reaction that is spontaneous. Okay, so again, we're always going to start at our standard conditions, and then we're going to look at, what is delta G from there. If delta G is positive, that's telling us we need to go in the reverse reaction. If delta G is negative, that's telling us we're going in the forward reaction. If we have delta G is equal to 0, like I said, that's really kind of rare, but that would mean that K is equal to 1, so we would be at equilibrium already. So delta G and K are directly related, right? They are inversely proportional. So the larger delta G is, the larger positive value of delta G, the smaller K will be. And if we have a really negative value of delta G, the larger K will be, right? Because if you think about positive values of delta G, that means we're going in the reverse reaction. So that means we are favoring the reactants. And so that would correspond to a very small value of K. If we have a very negative value of delta G, that's telling us it is spontaneous in the forward direction, which means it's favoring the products. Therefore, we're going to have a very large value of delta K. Of K. And then again, if it was 0, then that means K is equal to 1, and you would have, your forward and your reverse reactions being the same extent, essentially. All right, let's go ahead and try another practice problem. This one says calculate K at 298 Kelvin for the reaction, and we have that there. So we have some values of our delta G naught of formation, right? So these are standard Gibbs free energy of formation there, and we can use that to calculate our delta G naught and then calculate K. So at equilibrium, we have delta G naught is equal to minus RT natural log of K. So the first thing we need to do is find delta G naught, and we can do that from, these delta G's of formation. So we can go ahead and use that equation, products minus reactants, and plug that in. So then we will get our positive value for delta G, and we can plug this in and rearrange for K. So first thing we do, we'll divide by negative RT on both sides, and then the way that you get rid of that natural log is you do e to the on both sides, and that e will cancel out the natural logs. So you'll get e to the minus delta G naught over RT is equal to K, and you can plug everything in and then solve for your K value. Make sure, again, down here, that you are converting your units for R or converting your units for delta G naught to make sure that they match. That's probably the most common thing that people do wrong in these types of problems when everything else is going smoothly. Let's look at a different type of problem. So this one's a little bit more involved. So calculate K at 298 Kelvin, and we're given the delta G, so we don't need to calculate it from data like we did on the last one. And then it says a container is filled with, a bunch of different gases, and as you can see, they are not at 1 atm. So that's telling us we are not at standard conditions. So we're going to need to use that equation that has delta G, relating it to delta G naught plus RT times the natural log of Q, right? Because we're going to need to calculate Q. And then it says, in which direction, if any, will the reaction proceed to reach equilibrium? So we can look at our value for Q there and compare it to our value for K that we're calculating in that first part. To figure out whether, which direction our reaction will proceed, and then we can calculate delta G for our entire system. So lots of good stuff. Let's get going. So the first thing we need to do is calculate K, and we're given our value for delta G, so that's pretty straightforward. We can just rearrange this like we did earlier to solve for K. So we'll get negative delta G naught over RT and plug things in. Again, make sure to change your units and then you'll calculate that. Pretty straightforward. For B, we can now calculate Q since we have our pressures of a bunch of different gases, right? So we can plug that in to our reaction quotient and calculate our value for Q. And then when it's asking in which direction, if any, will the reaction proceed to reach equilibrium, we can compare our value of Q with our value of K. They are really different. Q is way smaller than K, which means that we don't have enough products, so the reaction will proceed to the right. So it's going to favor the forward reaction. And then in our last bit, we're asked to calculate delta G of our system. Since we are not at standard conditions, right, we have different pressures, so we'll need to use this equation. So we have delta G naught, which was given to us in the problem for part A, and then we calculated Q in part B, and so we can just plug that all in here. And sorry, this should say 8314, and then we can calculate delta G. So delta G is negative, which confirms, though, that we are going to proceed to the right to reach equilibrium. Remember, we can look at either delta G, right? To go to the right, delta G needs to be negative, and to go to the right, K will be very large, or Q will be less than K. All right, last one. So this says we have the oxidation of sulfur dioxide into sulfur trioxide. So we have a bunch of different pressures of gases, again, like we did last time, but the difference here is that we are not at standard temperature. We're at a higher temperature. So not only are we not at our standard states for our gases, right, we're not at 1 atm, but we're also not at 25 degrees Celsius. So we need to take that into account as well. So when we are calculating delta G, right, because we need delta G naught for that, we can't use our values of delta G naught from the back of the book. Like these are, listed here for delta H naught and S naught, but we can't use the values from the back of the book for delta G naught to calculate it because that is for 25 degrees Celsius. Okay, and so that's not going to help us because we need it at 225 degrees Celsius. Delta G changes a lot with temperature, but delta H and S don't very much unless there is a phase change. And so here it doesn't say anything about a phase change, so we're going to assume that none happen. So we can use our delta H values and our S naught values from the back of the book, and we can use that in this equation to calculate delta G. Okay, so we'll go ahead, we'll do products minus reactants to calculate our value for delta H, just like we've done before. And so we can get our delta H of our reaction, and then we can do the same thing with our S naught to get our delta S naught of our reaction, and we can do that. And then we can use those in this equation with the temperature, right, our 225 degrees Celsius that we convert into Kelvin, and then we can calculate our delta G naught. So please be really, really careful in a problem like this where you're like, I need delta G naught. Oh, I know how to find delta G naught. I'll just go to the back of the book. Well, you can't because we are not at standard temperature, okay? So we need to calculate it this way in order to get our delta G naught. Now we can continue on with the rest of the problem. Now that we have delta G naught, now we need to figure out Q, right? So we have this piece, we need to find this piece. So we can go through and calculate Q just like we have before, nothing different. And then once we have Q, we can use that combined with our delta G naught from the previous slide to calculate delta G. So we'll just plug everything in. Again, make sure your value for R matches your units for R match your units for delta G, and you can go ahead and calculate that. So delta G is equal to negative 91.9 kilojoules. And it says, in which direction, if any, will the reaction proceed to reach equilibrium? Well, we have a negative delta G, which is telling us that our reaction is spontaneous in the forward direction. Therefore, the reaction will shift to the right to reach equilibrium. And that is it for chapter 18. We've covered a lot of ground in this chapter. We've learned a lot about entropy and enthalpy and Gibbs free energy and how they are all related. And then in this last bit, we got to relate it back to all of our work we've done on equilibrium and reversible reactions. So as always, keep working through that chapter lecture worksheet. It's going to give you a lot of practice doing these types of problems, and it'll show you a lot of different ways that the problems can show up, and it will challenge you to think about the problems in some new ways. If you get stuck, please reach out to me and ask me your questions. I love to help, and I love talking about chemistry. So always, always, always ask me if you get stuck. But otherwise, keep working hard, and I will talk to you guys next time.